Hey guys, so this video is going to go over lesson 11.3 from day 3 of week 1 of unit 11. We're going to be covering Riemann sums. So you want to follow along with the handouts on the Google Drive. There's a classwork and then we'll go over the notes in just a moment. I'm just going to start big picture, kind of where we left off last class. So last class we talked about finding the area under the curve. So let's say we are measuring something like velocity and we have meters per second over here on the left and we have seconds here on the right and we had a straight line and I asked you to find the interval from 0 to 5, let's call this v of t, of v of t dt. All we'd have to do there is multiply 5 by 3 and find the area underneath this, and that would give us 15, and this would tell us from t equals 0 to t equals 5, 15 meters were traveled. Okay, so that was the big idea from 11.2, was just finding the area under the curve, getting a hang of integral notation. Okay, and so you might have slightly more complicated functions that are linear, something like this, right? Let's say if our velocity was not constant, our velocity head that was linear, but we can solve this the same way, right? We can divide this into a triangle and a rectangle and find the area that way. Okay, so where today's lesson went or goes is, instead of there being kind of linear geometric shapes, square, circle, triangle, we're looking at, well, what if it's not linear? What if it's a shape? Like this. So what do? I mean, we can't separate this into triangles and rectangles like we could previously, where it's very nice and clear. What do we do in this case? So what we do, this is where we'll go in the notes, is we do make rectangles. We actually do create rectangles. Now you'll notice that the rectangles that we create, they're not perfect, right over here. We go from the bottom up to the function and then to the right and then down and up to the function right and then down. And you'll notice there's some overlap here. So these rectangles, they're sometimes overestimating and they're sometimes underestimating. They're over approximating sometimes, like here, but they're under approximating here with this white space. But for right now, and where we're at in the course, this is the best idea we've got. So for example, I could draw rectangles on this curve, up, right, up, right, up, right, and so on. And I could approximate this area using a Riemann sum. Okay, that's the name of these rectangles. So let's read through the notes. Riemann sums are the name we use for when we use rectangles to approximate the area under the curve. We use sigma notation to represent the Riemann sums. First, let's look at an example. So here we are. So here we have this function x squared minus 6x plus 13, and we want to use 6 left endpoint rectangles to approximate the area under the curve. So let's just break down what does this mean? Well, approximate, that's the same sort of estimate, right? We're sort of guessing what the area is to the best of our ability using these rectangles. For x is greater than or equal to 2, x is less than or equal to 5, this is saying like the interval where we're going to do that. And then 6 left endpoint rectangles. We'll talk about left endpoint in a moment, but this is important. And then a lot of the times there are 6 rectangles of equal width. Often that's the case, not always, but often that's the case, especially for when we're talking about a function, which means that each of these has the same dimensions, right? Sorry, the same width, not same dimensions, but the width is always the same. So we have these 6 rectangles, each of them have the same width in this case, and so we need to the goal is with Riemann sums is you need to find the area of each of those rectangles. Well, how do you do that? Well, if you remember, the area of a rectangle is just base times height, right? So we need two things. We need the base and we need the height. So how do we find those? 1, 2, 3, 4, 5. Okay, I'll do a sixth one right here. So these are the six, these sort of blanks here are the six rectangles here. And each of them have a base and a height. Now remember, they all have the same width, the same base, right? And then we know there's 6 of them, and we know they happen on this interval. To find the width...
To set up your device using a screen reader, turn on Narrator by pressing Windows plus Control plus Enter. For more accessibility features, press Windows plus U, or select the...
To find the width, we take the endpoints, so this is our A and this is our B, and we divide that by the number of rectangles, n. So we do b minus a over n, and that will give us our rectangle width. So in this case, that would be 5 minus 2 divided by 6. That's 3 over 6. That's 1/2. That means that each of our 6 rectangles here has a width of 1/2. So I can go ahead and just add the 1/2 in here. Okay, so 1/2, 1/2, 1/2, 1/2, 1/2, 1/2. Those are all the bases. The heights change, right? This height is here, 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 this height is here. And you might be like, oh, okay, well, that's about 5, and that's what 4. I'm not sure what that is. That's 4 again, and 5, and maybe that's 6. And so you could kind of count that, but that's not exact, right? We don't know exactly where they're at the graph. We want the exact. Well, how do you get the exact? Well, we know the x value right here, right? And the height of this is the y value. It's f of x, where x is changing, right? So this is f of 2, and this is f of 2.5, and this is f of 3, this is f of 3.5, f of 4, f of 4.5. And that's what we put here. So we'd start with f of 2, then f of 2.5, then f of 3, then f of 3.5, then f of 4, then f of 4.5. You're like, oh, well, how do I know what f of 2, 2.5, 3, 3.5, 4, 4.5 are? Well, you would take those values and you'd plug them into the function here. So for example, f of 2, you'd plug in the 2, you'd get 4 minus 12, that's -8, -8 plus 13, that's 5. So this would be 5. Then you plug the 2.5 in, then the 3 in, then the 3.5 in, then the 4 in, then the 4.5. And the sum of that, that's the Riemann sum. Okay. So we can write this expression as in summation notation. To do that, we write the sigma, right? And then our starting point, which in this case is 0. And we will end at 5. I'll talk about where I'm getting these numbers from in a second. And then on the inside we have the argument, which will be 1/2 times f of 2 plus 1/2 times I. This expression equals this sum that I wrote above. Why is that? Let's talk about it. So, a general rule, we could use that sum to find the area. If we had more than 6 rectangles, this would be a lot faster to do than finding an expanded sum. We call this a Riemann sum, and it can be done with left endpoint, right endpoint, or midpoint rectangles. So left endpoint means taking it from the left here, like the height is the left side of the rectangle. Right means the right side is the endpoint, and then midpoint is right in the middle. Okay, these are the 3 forms. So we can have different shapes depending on whether it's left, right, and midpoint, and different approximations. Sometimes it's over, sometimes it's under, depending on which one you choose. These are written out as in sigma notation. So these are left-handed, and these are right-handed. um, what do these letters mean? Why are we starting at 0? Why are we starting at 1? Okay, so this delta x, this is the width of the rectangles, which remember we find that by b minus a over n. Right, I talked about that. That is the width. I think that probably makes sense to most everybody. That's b minus a over n. N, right, that's the number of rectangles. And you're probably like, okay, well, why is this I equals 0 and this is I equals 1, this is n minus 1, this is n. This starting at 0 and going to n minus 1, and starting from 1 and going to n, that's the same number of rectangles. It's just that this is basically saying starting on the left, and this is saying start on the right. And I'll show you why that is. On the right side here, we have the height, this f of a plus delta x times I. This is the height. This is the height. A is, again, it's our start. So if we start at 0, our first rectangle will just be f of the start point, right? So in this example, that's what we had, f of 2. Whereas if our first rectangle is 1, then our first, if our first rectangle was 1, then it would be the starting point plus the first width. So then you would be starting at, for example, 2.5 instead of 2. That's the Riemann sum. I'll do one example problem. So I'll do two. So first example problem might be something. I'll do something straightforward. F of x equals x squared. Find the Riemann sum approximation from x equals 5 to x equals 13 with 4 equal width rectangles and I'm going to mark here right for right-handed. So sometimes what's best to do is just to sketch out what's going on, right? What does x squared look like? X squared looks like this. So what we're going to mark is, okay, we're starting at 5, and we're going to 13 here, like this. And we're going to draw 4 rectangles that are right-sided between these. So it's going to look something like that. And it's kind of hard to see, there's 4 rectangles there. So first thing you're going to do is find the width. So again, the equation for the width is b minus a over n. Let's go ahead and label what a and b are. A is 5, that's our start point. B is 13, that's our end point. And n is the number of rectangles, that's 4. So this is going to give us our delta x, which we need. So 13 minus 5 over 4, that's 8 over 4, that's 2. That means each of my 4 rectangles is 2 wide. I'm going to write that out here. Okay, so I have my 4 rectangles, I'm making like space for them. And so one is 2, 2, 2, 2. Now I need the height. Well, I'm right-sided, right? I'm right side, it's a right-sided rectangle. So if you think about this, like, I'm going to zoom in on that graph for a second. We have 5, 6, 7, 8, 9, 10, 11, 12, 13. What's going on is, we have this curve, okay, and this is not to scale, but I'm just like kind of trying to show what's happening. We are determining the height based on the right side of the rectangle. So the right side of the first rectangle is not 5 or 6, it's 7. So it would be 2 times f of 7 plus 2 times f of 9 plus 2 times f of 11 plus 2 times f of 13. If I did a left-handed Riemann, it would be 5, 7, 9, 11. If it was a midpoint, it would be 6, 8, 10, and 12. That's where the numbers are coming from. So this is our Riemann sum. We just plug in 7, 9, 11, 13 in for x squared to evaluate this. Okay, one more I want to show you is like table. So the way tables work, usually it's something like this, and it might say like 0, 5, 3, 2, 9, 1, 10, -5, and then 13, 2. Okay. And it would say, like, find left Riemann approx. The way that we solve this is we look at those x values, and the distance between each x value will give us the width of the rectangles, and then the y value gives us the height. Sometimes it's helpful to draw this out. So for example, we have 0, 5, 3, 2, 9, 1, 10, -5, and then 13, 2, right? It's not too, it doesn't matter too much like where they go, but these are our points. When I say it doesn't matter too much where they go, these points aren't necessary to scale, it's just like to show us a visual what's going on here. For our left hand, we'd go from this point to here, from this point to here, from this point to here, and then from this point to here. Those would be your rectangles. So to find the value of those rectangles, we first find their widths between these x values, so 0, 6, 1, and 3, and then we're going to multiply that by their left, the left value. So it would be 3 times 5 plus 6 times 2 plus 1 times 1 plus 3 times -5. That would be the answer to this left Riemann sum with a table, and that's in the delta as well. Okay, I hope that was helpful, and we will go over this on day 1 this week.